Hi folks. So last time we were talking about A to D and D to A. And this time we're going to move on to another interfacing concept when we talk about sensors. We're going to talk about how we can use sensors, what sort of concerns that we've got when we interface sensors. So why do we need to worry about this? Well, it's the same idea as when we were talking about A to D to D and D to A, is that we've got the real world and we've got our microcontroller, and we need to be able to interact between the real world and the microcontroller. So our mechatronic system needs to be able to measure something that's going on in the world and then think about it and act on it. And so that measurement is going to include sensors, and then the action is going to include actuators. So right now we're going to talk about the sensors, how we measure what's going on in the real world, so that our finite state machine, that is the brains in our mechatronic system, can respond. So how do we distinguish between sensors and actuators? How do we classify sensors and actuators? Well, this would be another one of those discussion prompts if we were in the classroom. So things that you might think about is the method of action. How does the sensor or the actuator work, and how does it work relative to other sensors and actuators? When I say how does it work, is it a change in resistance? Is it a change in pressure? Is it a change in force? Is it a change in length? The different methods of action. What's the size of it? Is it big? Is it small? Is it heavy? Is it light? How does it fit into your robot? And then things like the response time and the input and output voltage levels or other characteristics. How do we build an interface between these things? How quickly does it work? So lots of different ways to classify them, distinguish between them, select among them. In general, when we've got sensors and actuators, we're thinking about changing physical properties. So we're going from some physical properties to some electrical or optical property, because electrical and optical properties are easy to deal with a microcontroller. And then the actuator is going to go the other way from the electrical or optical to some sort of physical property. And then we're typically moving with a sensor from something that could be high power density down to something that is definitely low power. And with the actuator, we're going to use a signal level or low power signal in order to control the power in our potentially high power actuation. So some physical property, high power, goes through our sensor and results in some sort of low power signal that will be conditioned as well. And in the actuation case, we've got some sort of power amplification stage that has an actuator, and that's all modulated by a signal level, the blue, that's coming from our microcontroller in order to provide some sort of mechanical work. So things that you might use in order to classify. You might talk about the sensitivity, which is the change in output compared to a change in input. We think about sensitivity as being something that we care about a lot with sensors. Also resolution, the smallest increment that you can detect. We're going to talk about that when we talk about analog versus digital sensors. And then dynamic range, how many of these small increments can we actually deal with? We might also talk about accuracy and precision and repeatability, and these are measures of how closely you can determine the true values. Are you consistently off by a little bit where you've got a little bit of an accuracy problem, but you get good precision? And then repeatability is the idea of precision, but applied to an actuator in this case. And linearity, is it nice and linear response between input and output, or is there a little bit of waviness? We might also talk about response time. How fast does a system respond, either a sensor or an actuator? And often these things will be first order type systems, which is going to be quantified by our time constant. If you think back to your dynamic systems class. We're not going to worry about dynamic systems class too much in this. But then you can also quantify that in terms of bandwidth, which is going to be your frequency response version of your time constant. That's kind of an awkward way to put it. It's related to your time constant in terms of frequency response. Input and output impedance, how are we going to connect these things together? We got to make sure that we don't load the system either mechanically or electrically, and that's going to depend on input and output impedance. So here is just an overview of some types of sensors you might see. So again, discussion prompt, if we were in the classroom, what type of sensors would you want to use for your project? You're thinking about your design project, so what do you need? What do you need to measure? How might you measure it? You could pause the video, write down some ideas, and then restart it. So we could have resistive sensors. So for instance, a potentiometer is a real easy way to measure rotation or translation. Or you could have a strain gauge that'll tell you deformation of your sample. These are operating on a change in resistance. We could deal with inductive sensors. For instance, an LVDT is using induction in order to determine a small displacement. We'll talk about this a little bit in the next section, but we're exciting the primary coil. We're looking at the mutual inductance as it induces voltage in the secondary coils, and then we're measuring that. We might also have proximity sensors that are based on induction, where we have an oscillator generating this field, and then some of the energy is absorbed as eddy currents into the target, and so it loses a little bit of power, which triggers your detector, and so you recognize that there's something there that's picking up this power. You might have a capacitive sensor. So for instance, this picture is from Physic Instrument. These little things are capacitive displacement sensors, and so they measure the distance in terms of capacitance between the sensor and the target. And so these are good for 15 micrometers, which is, it's really small. You could also do like this two parallel plate idea where you've got two sensors and you've got the parallel plate that moves back and forth between them, and so you can look at the distance and remember that your capacitance is going to be based on the area and the epsilon and the distance between them, and so as this plate in the middle moves towards one, the capacitance is going to change on both of them, and so you can measure that on both sides. You could have a piezoelectric type sensor. So remember, piezoelectricity is going to, well, it's got two effects. You can use it as an actuator or a sensor, but in the sensor case, there's some deformation of the piezoelectric element, and it is going to generate a charge, and then through our charge amplifier, we can convert that into a voltage. So for instance, you could have this compressive type accelerometer where the inertial weight is going to move, and it's going to compress the piezoelectric element. It's going to generate a charge. Alternatively, you could have a shear type or a beam type. There's different types there. But it generates a signal in response to motion, and so we can use that. We could also have magnetic, so this is Hall effect. We'll talk a little bit more about this one in the next section too, but for instance, you might have this sprocket going by, and every time one of those teeth is there next to the sensor, it's going to allow the magnetic field to reach the sensor, and then it's going to be detected as a change in the output voltage. So Hall effect is a great way to identify ferrous parts moving by. We could deal with optical sensors. These are the IR sensors similar to the ones that we'll use in lab. So in this case, we are bouncing a light off of an object and measuring the angle that it comes back, and that tells us how far away the object is. Alternatively, you can use a light source passing through a grating, and you can see that there's clear part of the grating and not clear part of the grating. So this light is coming full through onto the receiver, but this light is only coming half through onto the receiver. And so we can look at that as an encoder that tells us where the grating is as it moves back and forth. And we use that for rotation measurements a lot, optical encoders. We can measure temperature. So we've got RTDs, we've got thermocouples, we've got thermistors, we've got IR. So that's our IR. This is our RTD, and this is our thermocouple. Your thermocouple operates on the Seebeck effect, where you've got this dissimilar metals that are joined at the junction, and then this cold part is all in the circuitry. And so as it heats up, it generates a small voltage. Alternatively, you've got your RTD, which is going to have some sort of sensing wire. It's shown as platinum in this one, but there are other options. And that's going to change its resistance in a very known way based on temperature. And so that gives you high accuracy and high stability. We can measure light. So CCDs and CMOS, two ways that you've heard of to measure light. Think of them in cameras a lot. And then typically we've got these arrays of photodiodes, and then each of the photodiodes needs a filter on top, and so we might put together a filter on top of the diodes. So R, G, and B, so two Gs, one R, one B, and so each one of these elements, the R, the G, the B, each one of those is on top of a single photodiode, and so we can build up an array of RGB activated photodiodes so that we can have a color picture. And then one last thought here in terms of touch screens. We love our touch screens these days. So touch screens, we can have resistive touch screens. I don't see too many of these anymore, but this used to be a common way to do things, where we'd have these two layers, and then they be separated by these dots, and as you press them, you close that air gap, and it changes the resistance, and that's measurable. Alternatively, you might have something like this. This is a self-capacitive setup where we've got the, let's see, we've got these electrodes here, and you can see a bunch of little plates, and we've got a layer on top for us to touch, and so as we touch it, we make a parallel plate capacitor between our finger, or a stylus, and those electrodes, and so you can use that change there with a 555 timer to look at the step response, and so if you're looking at the step response, you can determine the RC time constant there, which will tell you what's going on and whether or not there's a finger because of the capacitance change. And then here's one more that shows up, is that you've got the two different lines going in a grid pattern. So you got the driving lines and the sensing lines, so each one of those makes little parallel plates at the intersection, and so touching them, you're going to add a second plate, so you've got a plate below and a plate above, and so now you can go through each one of those little intersections in sequence and determine which one of them is actually activated, and that's how you get that multi-touch capability. There's lots of different sensing modalities out there. You've got to figure out which one is appropriate for your particular application. Certainly I've seen applications that are going to be really suited to one sensing modality and not another, and it's up to you to figure out which is the appropriate type, but you got to make sure you know what the options are. So we will jump to the next video where we're going to go through analog and digital types of sensors, and we're going to look specifically at position and velocity measurements.